let's imagine a universe that is like a machine, like a clock. If you know the blueprints of this machine and you know the initial conditions, when the machine runs in time, then you will know exactly what's going to happen in the future. So it's a very boring universe, but we can imagine such a universe. In this universe, let's perform the following primitive experiment. So you have a black box, and you can have a particle that comes into this black box. You can press, the black box has two buttons, A and A prime, and you can press any one of them at will. Let's say if I press button A, then the incoming particle will give me the outcome, which is either plus or minus 1. The same applies to A prime. Now, because everything is deterministic, the particle has to have a set of instructions to tell this particle what to do if it encounters such a box. And it is not difficult to imagine that there are only four relevant instructions. So I listed them here. So suppose that, let's look at the instruction number lambda 1. So in this instruction tells the particle to do the following thing. If I press A, the particle will give me outcome minus 1. If I press A prime, the particle will give me the outcome minus 1 too. This instruction means that if I press A, the particle will produce outcome plus, and if I press A minus, it will produce outcome minus. And that's all. If you know which instruction, if you know that this particle carries one particular instruction, then you will know exactly what's going to happen. You get a well-defined, predetermined outcomes of your measurement, of your experiment with the box. But now suppose that for some reason, in this deterministic universe, I am not sure which instruction is carried by the particle. That's possible. For instance, if I flip the coin, if I know exactly how much force I'm going to apply to this coin, and I know the weight distribution of the coin, then I can predict exactly whether I'll get heads or tails. But if I don't control this, the power of my flip, and I don't know the mass of the coin and some other parameters, then I get apparent randomness, in which I get head and tails, if I'm very unlucky, equally distributed randomly, 50-50%. So suppose the same applies to this particle. So I'm looking at the box, the particle comes, but I don't know which instruction it carries. Those instructions are then, we can assume, distributed with some probability. Okay? For instance, it could be that each of them appears with probability 1/4. So they are equally distributed. Then if the particle comes, I don't know which instruction it carries, and then when I press the button, I get seemingly random outcome. So even in this boring deterministic universe, we can have randomness of this kind. Okay, ladies and gentlemen, now we are still in this boring deterministic universe, but we already saw that even in that universe you can have some randomness, and we complicate things. It's always good to complicate things to get something cool. So now this time we have two boxes. They are exactly the same boxes I described before. Two buttons, A prime, B prime, and outcomes A prime, B prime. But this time two boxes, so there are two particles, and those particles originate from some source. It doesn't matter what it is. One flies to Alice, one flies to Bob, and at the source those particles can be correlated, or in our universe they are given, when they fly, before they fly, they are given a set of instructions what to do when they encounter such boxes. So here is the set of such instructions. Let's say instruction lambda 1. It means that the particle that flies to this box will give me answer -1 if I press button A, or -1 if I press button A prime. And this box will give me outcome -1 if I press B, and -1 if I press B prime. And let's look at the second instruction that they can carry, those particles. Again, if Alice presses or A prime, she gets minus outcome. But Bob, if he presses B, he will get, we call them Alice and Bob. If Bob presses B, he will get outcome -1. If he presses B prime, he will get outcome plus. And you can easily check that there are only 16 such instructions. So that's the whole set of relevant instructions to describe what can happen in this experiment. And again, like before, if I know that this pair is carrying instruction lambda 2, let's say, then I don't even have to measure anything. I don't have to even press any buttons. I know exactly what the boxes are going to give me. It's that boring. But if I am uncertain about which instruction is carried by any given pair that flies to Alice and Bob, then, as before, I have to assume that there is some probability distribution of those instructions. And so this is P of lambda when lambda is one of those instructions, and here maybe it is better to write it like that. P of lambda is a shorthand notation, but this is more meaningful notation because here you exactly know what outcomes appear with what probability. And now let's analyze this experiment and see what we can get out of it. All right, so we discussed this experiment with 2 boxes and 2 particles, and we decided that we described that experiment in our boring deterministic machine-like universe by those set of instructions lambda, which is a string of 4 ± 1 numbers, A prime, B prime. And our ignorance, our randomness comes from not knowing which instruction is carried by a given pair of particles. So that's why we have the probability of getting a given instruction. It's all very beautiful, simple, and nice. Now, a little bit of mathematics. It's not difficult, but it's necessary to get a very fundamental thing that you will learn today about this deterministic, boring machine-like universe. All right, so what we have here? So we have this strange-looking symbol, which we call a correlation function. It is defined in the following way. So you multiply outcomes A and B for Alice and Bob, and you multiply them by the probability of the instruction that contains those answers. So you sum over all possible instructions such that you get all possible answers for Alice and Bob if they press button A and B. And this function tells you roughly how well or how bad outcomes A and B are correlated. Okay? So I don't want to get into details, but this tells you somehow how well those particles are correlated by the set of instructions that they carry. And we define those correlation functions for all possible configurations of the buttons that Alice and Bob can press. So they can press A and B prime, A prime B, or A prime B prime. There are no more options here. Now, so let's take those simple equations and let's take those average values, those correlation functions, I'm sorry, and let's add them like this. So we take this one plus this one plus this one minus this one. You see, this minus is very important, and that was contribution of John Bell, who actually realized that you need this minus to learn something about that deterministic universe. Right, so we have this expression, and let's replace those correlation functions by the formulas here. Again, looks intimidating, it's really simple. So, summation over lambda, we take this P of lambda outside, and the meat of the whole argument sits in this bracket here. So you see that these are outcomes of your measurements, And they follow this pattern that tells you which buttons were pressed. So A, B buttons pressed, out comes AB. AB prime buttons pressed, out comes AB prime. And so on and so forth. Now, this number here, so A and B, all this A prime, B prime, are plus and minus 1 numbers. Let's group them together. So the grouping is like that. We have A plus A prime times B plus A minus A prime times B prime. And this grouping is very nice because now you see that if, for instance, A equals plus 1, A prime equals plus 1, and B equals plus 1, this here will be 2. But this will disappear because it was 1, 1. Here we have 1 minus 1. So it just is gone. All right? Or another example. Let's say that A is plus 1, A prime is minus 1. Then this will disappear no matter what B is. But this one will be 1 minus minus 1, which is 2. And if I put B prime equals to plus 1, then I will get 2 again. If you look at all possible configurations of those plus minus outcomes, you will see that this expression in the square bracket can be either plus 2 or minus 2. There are no other options. And now because you multiply this plus minus 2 by probabilities, which are numbers that are positive and between 0 and 1, this sum here cannot exceed plus or minus 2. So this expression here cannot exceed plus or minus 2. But this expression is this one, so therefore this expression is always between minus 2 and plus 2. And that's the property of this universe we discussed with this particular box experiment. That's the essence that we need to discuss further. Okay, now, ladies and gentlemen, magic is gonna happen. So, in boring universe, we considered a very simple two-box experiment, and we concluded that the logic of particles carrying some instructions on what to do forces us to this inequality. So this inequality, called Bell inequality, or to be more precise, QuTalent inequality, is the essence of this two-box experiment in the boring universe. I'm sorry, I'm repeating myself, but that's the gist of what you have been listening to for the last 10 minutes. Now, let's go quantum, because that's what we can do in the laboratory. So in the laboratory, we can set up a similar experiment, details of which I will kind of skip, because that would be too boring, and I don't want to bore you guys. So, we have boxes with 2 buttons. You can press either A or A prime, B or B prime, and again, you get the answers plus minus 1. But this time they are real quantum boxes, which correspond to some experimental apparatus you can build in the real laboratory. These are not some abstract boxes we discussed before in the boring universe. These are the real ones that you can construct in the laboratory. And now, the particles that fly to those boxes are quantum particles, and quantum mechanics tells us that such pairs of particles are described by what we call the wave function, psi. Again, doesn't matter what it is, wave function describes all we know about quantum particles originating from some source and flying to Alice and Bob. Now, when Alice and Bob perform this box experiment in exactly the same way as we discussed in our boring universe, they will see that after calculating their correlation functions, I put letter Q here to distinguish them from the correlation functions that we considered in the boring universe, then they will see something absolutely remarkable. They will see that this value here is 2 times root 2. And 2 times root 2 is greater than 2. So therefore, quantum universe does not obey this Bell QuTalent inequality. It just doesn't. And this is experimental fact. This year, Nobel Prize winners conducted such experiments in the laboratory, and they get this value here. So they confirmed that we are living in a quantum universe, not in the boring deterministic universe as we described before. Now, but what does it mean that this is 2 root 2, which means that I violate this inequality? Well, it means that those quantum particles that fly to Alice and Bob, they do not carry any instructions of what to do when they encounter such boxes and choices of buttons by Alice and Bob. Such instructions are incompatible with nature, incompatible with what you see in the laboratory. All right? Sorry for that. So, is it strange? Well, it is mind-boggling because in our life, such instructions are always there. Things that we see in our world, let's say, I see my watch, I see my car, those things that we observe in our world, they are always governed by a set of instructions of that kind that I described in that toy model boring universe. But at the quantum level, this is not true anymore. So there's a big discrepancy between microscopic quantum world and macroscopic world that we are living in and we can feel and touch. And, you know, well, Nobel Prize was given for this kind of deliberations, which is really absolutely